Hello again, welcome to the course on biostatistics and design of experiments. In this class we are going to briefly touch about various statistical tests that needs to be one should understand and how to go about using them. So, there are different types of statistical tests, some are used for comparing mean of data, some are used for comparing variance of data, and some are used for comparing ratios of data and so on. So, we will talk about that. So, before going into that let me recall again how you go about doing this hypothesis. You have something called the null hypothesis, which is no difference or status quo. So, imagine I am comparing the IQs of two different classes or class of students, then I would say the null hypothesis will be there is no difference in the IQ of students in class A and class B. Okay. Then we have the alternate hypothesis. So, if I am going to say yes, there is possibly a difference, then I would say the alternate hypothesis will be the IQ average of class A is different from IQ average of B. Okay, then you can also have another situation where instead of just saying different, the IQ average of class A could be better than the IQ average of class B. Okay, that is we are comparing only the better part of it, and or the IQ average of class A is worse than that of that class B, that we are then comparing only the worst part of it. So, we have those three situations. No difference is the null hypothesis, there is a difference is the alternate hypothesis, and that is called a two-tailed comparison. There is a difference, it could be greater or worse. Then we are comparing only one side of it, greater side of it or worse side of it, then that is called a one-tailed test. Okay. So, we decide on the hypothesis with the tail, and then we also decide on the p-value, that is am I going to test against 95% confidence or am I going to test against 99% confidence. So, p of 0.05 indicates 95% and p of 0.01 indicates 99%. Okay. Once I decide on all these, that means I decide on the type of hypothesis, I decide on whether it is a single tail or a two tailed test, then I decide on the p I want to look at, then I calculate using different tests something called t, and then from there I will calculate maybe the p value, and then I will say whether the p value which I have calculated is less than 0.05 or it is more. So, if it is less than 0.05, obviously there is a difference. So, obviously I cannot accept the null hypothesis, I have to reject the null hypothesis, that means I have to accept the alternate hypothesis. Now, if the p value is greater than 0.05 for a 95% confidence, obviously there is no reason for me to reject the null hypothesis. Okay. Okay. So, if imagine I am testing two drugs in the market, okay, which affects the sleeping pattern. So, the null hypothesis could be there is no difference between the two drugs. Okay. The alternate, there is a difference at a 95% confidence interval. Now, what type of hypothesis equations we will put for the two tail and a single tail. For a two tail, your alternate will be mu A is not equal to mu B, your null hypothesis will be mu A equal to mu B, that is a two tail. For single tail test, null hypothesis could be mu A is equal to mu B, alternate hypothesis could be mu A is greater than mu B. That means drug A has an increased effect on drug than drug B, or mu A could be less than mu B, that means drug A has a decreased effect than drug B, that is a lower tail and upper tail. Okay. Now, there is something called error. There are two types of error. There is something called type 1 error and there is something called type 2 error. What is type 1 error? We are rejecting null hypothesis H naught when H naught is true. That means we are rejecting the null hypothesis, whereas in reality the null hypothesis is true. That is called type 1 error. Then you have the type 2 error. We fail to reject the null hypothesis when the alternate hypothesis is true. okay, whereas instead of accepting alternate hypothesis we do not accept alternate, we accept null hypothesis. So, we have two situations. So, we have one is called the do not reject null hypothesis, reject null hypothesis, null hypothesis true, alternate hypothesis true. So, here this is the correct, null hypothesis true, you do not reject null hypothesis. Similarly, alternate hypothesis is need to accept, reject null hypothesis. So, this is a correct situation, whereas in sometimes although we need to null hypothesis true, we end up rejecting the null hypothesis, okay, that is called the type 1 error or alpha error, okay. Whereas in the other situation we do not reject the null hypothesis, whereas we have to H1 is true, that is called the type 2 error and that is called the beta error, okay. So, type 1 error is generally the probability 95% or 99% or 90% which we make use of in our statistical calculation, okay. Okay, that is where if you take larger alpha, then obviously you are very sure that you will not reject the null hypothesis, okay, where when H naught is true, but then your significance level also gets affected by that. So, this table is very important. When H naught is true, okay, we reject the H naught, okay, that is called the type 1 error. When H1 is true, we fail to reject the null hypothesis, that is called the type 2 error or beta error. So, type 1 error is called the alpha error and type 2 is called the beta error. So, we need to always sort of balance between the alpha and the beta error, and generally we give more importance to the alpha error actually. Okay. So, as you know, we have continuous data and alternatively we have the discrete data. Discrete data we use equations like binomial or we use Poisson and so on. So, when we have the continuous data, there are many situations, okay, we can have one sample, that means I know the population details, I take a small sample and I am comparing with the population, that is called a one sample. For example, I know the 12th standard average from a particular school is 95%. So, I take 10 students in that school and calculate their 12th standard average, I may get some x bar. Now, I want to know whether this x bar is related to the 95% school average, which is more like a population, or is it very far away. So, here we are collecting only one set of samples and then comparing with the population, that is called a one sample test or one sample t test. Okay, here we are comparing the mean of the sample with the population mean. Now, what is two samples? Suppose I am comparing drug A and performance of drug A and performance of drug B and trying to tell there is no statistically significant difference between their performance or there is a significant difference. That means I am comparing means of two samples, that is why it is called the two sample t test. Now, again you can have multiple samples, I may be comparing drug A, B, C, D, so I could be having lots of different means, okay. That is called multiple samples actually. Okay, so there are many ways by which one could analyze this data. One is called the studies table, okay, run chart, then we can look at the shape, we can create a histogram and see whether it looks normally distributed, okay, then we can look at the data whether it is and so on actually. And then there is something called a chi-square test, okay, and then there is something called a t test. T tests are generally meant for comparing means, chi-square tests are generally meant for comparing ratios, and there is something called F test which is generally meant for comparing variances or spreads actually. In the t test we have three types of t tests. One sample t test, that means I take only one sample and then compare it with the population, or I can have a 2 sample t-test where I am comparing 2 sets of samples, or I may be comparing pair t-test. That means there is a relationship between the sample items with A and sample items in B. Okay. So, when I am comparing variances, there is something called F test, or if I am having multiple samples and I am comparing variances, then this is something called ANOVA, analysis of variance test, and if I am comparing the spread, there is something called homogeneity of variance. So, there are different types of tests that are possible, and we are going to spend a lot of time on each one of them actually. So, we can have only one sample collected, comparing it with the population, or we could be having 2 samples collected, comparing with the population. We could have multiple samples collected, comparing with the population. Okay. Then if I am comparing means, then there is something called t-test, the 1 sample t-test, the 2 sample t-test, pair t-test. If I am comparing variances, there is something called F test. If I am comparing variances of a large number of data sets or samples, this analysis of variance. If I am looking at spread of the data, I can use something called homogeneity of variance, and so on. So, large number of tests are possible. We will talk about each one of them in detail, and we are going to spend with some examples also. So, do not worry about it. Okay. Okay. So, if we are comparing means, there is something called t-test. So, we can get a average of sample 1, and then I get a mean of sample 2, okay, and then I am going to find out whether both the means come from the same population or each of the mean come from 2 different population. Okay. It is called a t-test. T-tests are quite robust even for normal data. Okay. Generally we can say the standard deviations have to be similar, but there can be some difference in the standard deviations also, but still t-test is good. So, in t-test we have 3 types: 1 sample t-test, 2 sample t-test, and pair t-test. So, 1 sample t-test, you are taking a sample out, and then you are getting the mean and the variance of that sample, and you are comparing it with the mean of the population. Like I gave you some examples actually, I take 10 students from a class and then get their mean average, class average, the marks average, then I compare it with the school average and try to tell whether these averages are far away from the school average or they fall into the same population. Okay. I can do that sort of study. I can collect IQ of 10 students in a university and then try to say whether their mean IQ falls within the university average IQ or it falls outside that. So, that is 1 sample t-test. Here we are taking only 1 sample. 2 sample t-test, if I am going to have 2 sets of samples, I am taking 10 students from one university, 10 students from another university, and getting their IQs and then comparing their IQs and trying to say whether the IQs are statistically different or there is no statistically significant difference between these 2 IQs. Okay. So, that is called 2 sample t-test because I am using 2 sets of samples. Pair t-test. Okay. So, if you are pairing 2 sets of data, then expected result, difference in result should be 0. For example, I take 10 cats and I test a drug A on the 10 cats and look at the outcome. Then on the same 10 cats I give drug B and look at the outcome. So, the difference should be 0 if there is no difference between the drug A and drug B. Okay. If there is a statistically significant difference away from 0, then I can say yes, drug B A is different from drug B because I have used the same volunteer cats and I am testing drug A, seeing some performance change, then I am testing drug B, seeing some performance change. If drug A and drug B have to be same, then the performance change we observe, the difference in performance change we observe should be equal to 0. That is called the pair t-test. So, we are going to look at examples of each one of them. So, you do not worry about that. So, interestingly, all these tests are looking at means, that means averages, average or mean of the samples which you are taking it out, okay, whether it is one sample t test, two sample. Now, you may ask the question, suppose instead of 2 samples, if I have many more samples, what will I do? Of course, I can take two sets of samples one at a time and do a 2 sample t test, but there is another approach which is much faster, that is called the ANOVA, analysis of variance. It is called the one way ANOVA. We will talk about that later in the course. Okay. Now, if you are comparing variances, that means you are comparing the standard error. So, here we are comparing variances, and this is generally valid both for normal and non-normal. So, the H naught will be sigma 1 square is equal to sigma 2 square and so on. Okay. We cannot reject H naught when p is greater than 0.5, and alternate could be sigma s square is different from sigma p square blah blah blah. P is less than 0.05, we have to reject H naught and accept HA. So, you see the tests are there for comparing variances. So, in the t test we are comparing means, here we are comparing variances. One test that is there is called the F test. That means I am comparing the variation from a sample 1 and a sample 2. Okay. So, the H naught could be sigma 1 square is equal to sigma 2 square, that means variances are same, or the alternate could be sigma 1 square is different from sigma 2 square. So, we calculate the F ratio which is given by S1 square by S2 square. S1 and S2 are the sample okay, standard deviation. So, S1 square is the variance. So, there is a table called F table for a 95% or 99% you will get F value, and if the table F value is greater than the F you calculate, then you accept H naught. Okay. If the table F value is less than the F you calculate, you reject H naught and accept HA. Okay. For different degrees of freedom, the degrees of freedom for data set 1 is n1 minus 1 if you have used n data sets, and degrees of freedom for data set 2 is n2 minus 1 if you have collected n2 samples. That is called the F test. And then you also have ANOVA when you are comparing a large number of data sets. In the previous F test we have only 2 data sets, 1 and 2. So, you are saying sigma 1 square is equal to sigma 2 square, alternate is sigma 1 square is not equal to sigma 2 square. So, ANOVA is very powerful because we can collect a large number of data sets. I am comparing the IQs of University A, University B, University C, University D, and trying to find whether there is a statistical significant difference or not. I am comparing drug A, B, C, D in clinical trials, and I want to perform analysis to find out whether there is a statistically significant difference. Then I use ANOVA here. Okay. The variances of the samples are approximately equal, the response within any given level are normally distributed. These are the assumptions. So, H naught will be all these are same, whereas HA is at least one variance is different. Okay. Then you get a p value less than 0.05. Okay. So, we have the t tests, different types of t tests which are very powerful for comparing mean. Then we have the test for comparing variances like F test and ANOVA, and then for ratios we have something called chi-square test which we will talk about later. So, if there is something called the power of the test, or the if H1 is true, so that the distribution of X is specified by H1, then the probability of rejecting H naught is the power of the test for distribution. Okay. H1 is true, so you have two situations, you do not reject H naught, that is the beta error, whereas you reject H naught. Okay. So, if H1 is true and you reject H naught, that is called the power of the test for that distribution. Okay. So, you have two types of errors, alpha error where you should not reject H naught, but you end up rejecting H naught. Okay. whereas the beta error you have the you have to reject H naught, but you do not reject H naught, and that is also called the power of the test. Okay. The beta error is also called the power of the test. So, these two terms are very important when you are deciding on the alpha error and the beta error. Okay. Let us get into problems. The first problem is called the one sample t test one sided. Okay. So, the average size of barnacle shells is 25 mm. You know what is a barnacle, right? It is a marine organism, it has got a shell, it gets attached using a glue to hard surfaces, and then it feeds on it. Okay. So, it has got a shell and average size is 25 mm. Now, we have collected 10 barnacles in South India and we got their sizes. Okay. These are the sizes. Now, are these South Indian barnacles of smaller size? Okay. That is the question, or they are of greater size. So, we take 95% confidence. So, this is the South Indian barnacles, the average comes out to be 24.4, but the population average is 25 mm, that is this statement. Okay. Now, I want to know whether the this 24.4 is statistically significantly smaller or it comes from the same population at a p value of 0.05 or a 95% confidence. So, how do we do that? Simple, H naught is equal to mu naught. Okay. That is mu naught is your original mean of the population. Now, they are same, but alternate is mu is less than mu naught. That means you want to know whether the average size of the barnacle shell from South India is less than this 25. So, what do? You calculate T. If you remember this equation, we had this mu is equal to x bar plus or minus T into S by square root of n. So, we rearrange that to get this T value, x bar minus mu naught divided by S square root of n. It has got a degrees of freedom n minus 1. If T which we calculate is less than the table T. So, there is a table T for different degrees of freedom except H naught. If T is greater than T than the table T, then reject H naught. This is called the of course, we are using one tail test. Okay. So, what do? We get the average which is 24.4, we get the standard deviation which is 2.59. Okay. So, the T calculated we can use here, okay, 24.4 minus 25 divided by S divided by square root of n. So, we get the T calculated minus 0.73. For 9 degrees of freedom, T table, there is a T table here. So, I want you to look here. For 95%, this is a two tail test and the top one is a single tail test. In our problem, we are talking about single tail test because we want to know whether this South Indian barnacles are of smaller size. Okay. So, for 9 degrees of freedom, you go like this, you go like this and read out 0.05 here, you get 1 point for 9 degrees of freedom 1.833. So, T table is 1.833, the T calculated is minus 0.737. So, T calculated is less than the T table. So, there is no reason for you to reject H naught at this condition. So, what you can say is the South Indian barnacles, there is no statistical reason for saying that South Indian barnacles are of smaller size. So, South Indian barnacles come from the same population of 25 mm. In order to get a confidence limit on the mean which we calculated from the sample, as you know this equation mu is equal to x bar plus or minus Td of S by square root of n. The S by square root of n is called the standard error, right. I talked about this long time back. Now, you need to know the degree T value. Now, for these you have 10 data sets, so obviously degrees of freedom is 9, you get T as 2.26 and the mean of this sample is 24.4. So, 24.4 plus or minus 2.26, the standard deviation is 2.59 divided by square root of 10, which is equal to 24.4 plus or minus 1.85. So, the confidence limit 95% confidence limit for this mean is 22.24 to 26.25. One important point you need to remember is the t which you calculated will be for two tail both the sides, because we are talking about plus or minus, that is why we get 2.26. 4 mm as the mean of the sample with the standard deviation of 2.59, and you want to know whether the mu which you calculate is equal to mu 0, the alternate mu is less than mu 0. So, for mu is equal to mu 0, what do? We calculate the t, you know t from this equation, if you adjust it is okay, x bar minus mu divided by s square root of n. Okay. So, you get minus 0.73 7377. For 9 degrees of freedom we have from the table I showed you t table, the top one is for single tail, the bottom one is for two tail. So, for p of 0.05, 9 degrees of freedom you get 1.833. So, obviously the t which you have calculated is much less. So, there is no reason for you to reject the null hypothesis. For 95% confidence we say 24.4 plus or minus 1.96, s is equal to given here 2.59 divided by square root of n. So, you get the confidence limit for the mean is 22.8 to 26. So, obviously your 25 falls within that, that is why you are not able to reject the null hypothesis at this condition. Okay. So, this table is very important, as you can see this table gives you for different degrees of freedom, the top one for single tail, the bottom one is for two tail. So, if I am interested in a single tail I will use 95% this column, if I am interested in two tail 95% I use this column. Okay. As you go down as you can see for infinite degrees of freedom we get 1.96. Okay. So, as I said two tail 0.05 means a single tail 0.025, because when you say 95% two tail the tails are divided half on both the sides, that is why you get 0.05 by 2 which is 0.025 here. Do you understand? Do you understand the logic of this particular table? This table is very important when you are calculating t test, when you are calculating t based on means, whether it is one sample t test, the example which we saw, or later on we are going to look at two sample t test, pair t test and so on. So, this table is very important. So, that you calculate t from the equation, okay, then you calculate t from the equation and then you compare that with the t in the table, okay, for a different degrees of freedom, and then you say whether the t calculated is greater than t table. If it is greater, then you can reject the null hypothesis, but if it is less, t calculated less than the t table, you cannot reject the null hypothesis. Okay. Now, we can also use the particular software which I mentioned about, the GraphPad software which can also calculate the t value, okay, given the probability value. See, you can see for a one tail it is 1.833. So, you compare with the t which you calculated, okay, which is minus 0.737. So, there is no reason for you to reject the null hypothesis. But if I take t value, okay, the minus 0.737, and then the same software can be used to calculate the p value, the p comes out to be 0.479. So, obviously you can say it is not statistically significant at all, it should have been 0.05 or less, then only we can call it a statistically significant difference. Okay. So, it is very useful for calculating this, okay. Or we can also use one sample t test results, again the GraphPad software can do this, and again the results, as you can see, it gives you a p value of this, the difference is considered to be not statistically significant. The actual mean of the sample is 24.4, the hypothetical mean you want to reach is 25.0 and so on actually. Okay. So, we will see how to do this. it is quite simple. We have this data set, okay. I will show you how to do this. So, here we have the continuous data. Here we need to use this particular thing. Okay. Here you have the one sample t test, as you can see here, one sample t test, you can say continue. So, we can even enter data like this, or we can enter copy paste like this. Okay, so, we can enter the data like that also. So, I am comparing it with respect to 25. 25 is my population. Now, I want to know the sample which is equal to 22 and so on. So, I can copy this, and I go to my, I paste it here. Or if it does not get pasted, so obviously we can write so we can write 22, 23, 22, 25, 28, So, we say 22, then we say then we say 23, then 20, 22, 25, 28, 25, 28, 27, then again we put 28, then again we put 25, then we put 23, so we have 10 data points. We can put this here and then we can say calculate now. So, here we put 25 is the global average which you are interested in. So, we can say calculate now. Okay. So, by conventional criteria the difference is considered to be not statistically significant because the p value is coming out to be 0.4826. So, if you get a p value less than because the t value is 0.732, whereas you want 1.833, so obviously it is not statistically significant different. So, you can use the GraphPad software also to calculate. You can put in your data and you can use the GraphPad software also to perform this type of calculation. Okay. So, it is quite a useful software, and this problem is quite simple. So, you have the population mean and you have the sample. So, from the sample you calculate the mean, from the sample you calculate the standard deviation, and then you calculate the standard error which is given by s by square root of n, and then you can get the t value, and then for 9 degrees of freedom you make use of this particular table, and for a single tail test, okay, for a single tail test you use this. So, you go like this, for 9 degrees of freedom you get 1.833, whereas t calculated is 0.7377. So, obviously we have no reason for rejecting the null hypothesis, that is what it is. So, I showed you how to calculate from the GraphPad software also actually. Okay, we will continue more on this one sample t test as we go along. Thank you very much for your time.